So, like I mentioned a second ago, um, we are going to go through some examples of the three types of energy that we talked about last class. So, the three types that we talked about were kinetic energy, and the equation for that is going to be 1/2 times the mass times the velocity squared. Then we talked about gravitational potential, and that's going to be mass times gravity times the height. And then lastly, we talked about U elastic, and that's just going to be 1/2 times the spring constant times the stretching or compressing of the spring squared. So if you guys have not written down these equations, I would highly recommend it. They're going to be very useful. And because the algebra is very easy with these equations, like solving for any particular variable, essentially what's going to be going on is you're going to have one of these equations, or I'll say you'll have two of the three of these, and then you're going to be solving for one of the variables that's inside of it. So you would have like kinetic on one side, and then you grav on the other, then you substitute in, and then you solve for one of the variables. So being honor students, I think that you guys are more than capable to do that. But for today, what we're going to do is we're just going to have basic examples of I give you a mass and I give you a velocity, and then we figure out the kinetic energy. I give you the mass and I give you the height. We figure out the gravitational, and I give you the spring constant, and I give you how much the spring has been compressed or stretched, and then we figure out the U elastic. That's all we're going to do today. It's very simple. It's essentially just plugging into the equation and then getting a value. Cool. So first off, we're going to talk about kinetic. So if I've got a car and it looks like a little top hat, but the car has a mass m, and it's also going to have a velocity v. And the objective is to figure out what is the kinetic energy of the vehicle. Cool. All right, let me get Kimon. Did anybody else come in? Jaylee, thank you. Brian, Jacob, Jackson, Nathaniel, Sean. If you guys are here, let me know in the chat. If not, then you're going to be marked absent. Okay. So if I claim that the car has a mass of 2,000 kilograms, it's a beefy boy, and it is traveling with a velocity of, we'll say, 60 meters per second. So not only is it a beefy boy, but it's moving pretty quick. So my objective is I want to figure out what the kinetic energy is of this vehicle. So I just use the kinetic energy equation, which is 1/2 times the mass times the velocity squared. My mass is, so before I plug in the values, I like to do this just to make sure that all my arithmetic is correct. So I plug in the mass as 2,000 kilograms, and then the velocity as 60 meters per second. Cool. So if I put that into the calculator, now technically I shouldn't need a calculator, but it is early in the morning. Where's the square? Yeah, whatever. All right, so the amount of energy that I get is 3,600,000 and what are the units? So we haven't talked about the units yet. Now, let's try to figure out what those are. So when we talk about energy, spoiler alert, the units are called joules, right? Not J-U-U-L, J-O-U-L-E-S, joules. So mass has units of kilograms, velocity has units of meters over seconds. So we're going to have kilogram times meter over seconds, but the velocity is squared, so we also have to square the units. Okay. So if I distribute the square to the meters and to the seconds, what I get is meters squared over seconds squared. Okay. So if we remember back to forces, a kilogram times meter over second squared this would be a Newton, but then I still have that extra meter over here. So we have a Newton meter, which is what we refer to as a joule. Okay. So we're going to have 3,600,000 joules. So 1, 2, 3, 4, 5, 6. So it might be easier to write this in scientific notation. So we get 3.6 times 10 to the 6 joules. So another common unit would be kilojoules. So if I have this, the 3,600,000 joules, if I want to express this in kilojoules, I would just move the decimal 3 points to the left. So that would be 3,600 kilojoules. So that would also be a correct answer. Does anybody have any questions so far? All right. If nobody has any questions, I can move on to the next problem. All right. So the next example is going to be gravitational. So in this situation, make it a little bit cleaner. Hux. Okay, so if I've got a ball and it is a certain height from the ground, and the ball has a certain mass, and we are releasing it from rest, so there is no initial velocity, and he's got a really long arm. I want to know what the gravitational potential energy, the instant right before I let it go. So right before, not after. So the instant right before I'm getting ready to let it go, I want to know what the gravitational potential energy is. Because by the time this ball comes down and hits the ground, all that energy is going to be converted into kinetic energy or energy of motion. So I want to know what that kinetic energy is in the second part of the question. But we're going to do that on another day. We're just trying to figure out what the gravitational potential is. So my goal is to solve for ugrav. And I'm given that the mass, we'll say, is 15 kilograms. We know that the acceleration due to gravity in my class is going to be 10 meters over seconds squared. And then we're going to say that the height is going to be 100 meters. Cool. So the equation for gravitational potential is going to be m times g times h. And then I literally just plug in. So again, I like to put the parentheses as placeholders. So the mass is going to be 15. Gravity, or acceleration due to gravity, is going to be 10, only in my class. And then the height is going to be 100. So what we end up with, it's going to be what, 150,000? Sure, it's 150,000? $1,500. You get an extra zero in there, Josh. So an easy way to double check is if I multiply anything by 10 or like 100 or 1,000, I just count the zeros. And I just put the number of zeros behind this number. So 15 times 10 times 100, there's 1, 2, 3 zeros. So that would give me 1, 2, 3 zeros, and then so it'd be 15,000. 15 times 10 times 100. Okay. I was like, I mean, I got it right here. I don't know if you can see it or not. Okay. So this, of course, is going to be units of joules. But just to verify and kind of prove to you guys that it is, in fact, joules, we have mass, which is in kilograms. So what I'm going to do is I'm going to take this and I'm just going to multiply the units together. So we've got kilograms times meters over seconds squared, because that's the unit of acceleration, and then times the meters for the height part. And remember, kilograms times meters over seconds squared, that is a Newton. And then we have the meter. A Newton meter is a joule. So that checks out. All right, so my gravitational potential energy, in this case, it's going to be 15,000 joules, or more commonly, we can express this as 15 kilojoules. Remember, kilo means to the power of 3, or positive 3. So you just divide it, whatever your value is, by 1,000 to get it into kilojoules. Cool. Easy stuff, right? Any questions? All right. And lastly, we're going to deal with elastic. I apologize for the creakiness of my laptop stand. All right. So in this scenario, we're going to have a spring that is going to be stretched a certain distance. So we want to figure out U elastic, or the elastic potential energy. And so this would be the rest state. So in other words, the state in which I'm not applying any kind of external force to the system. So this is the spring and the block just sitting there on the surface. And then this part is or I'll say stretched. So this is the part where it's stretched. And with U elastic, to figure out the elastic potential, if I go back up and look at the equation, this one here, there is the spring constant, and then how much the spring is either stretched or compressed. So those are the only two things that you need for U elastic. So for the spring constant, this is going to be a lowercase k, we're going to say that it is 600 newtons per meter. That's pretty reasonable. And remember that the spring constant, all that is how much force is required to stretch that particular spring a distance from its rest length to stretch it a total distance of 1 meter. How much force is required to do that? That's all the spring constant is. If it's a stronger spring, I would have to apply more force to get it to stretch to 1 meter. Make sense? If it's a softer spring or a more loose spring, it would require less force to go that 1 meter. So this is the spring constant. And then the delta x. Now, this delta x is the displacement of the spring. Like how much was the length of the spring changed? Now, it's represented by a delta x, but I want to make it explicitly clear that this x does not necessarily mean change in the x-axis. This literally means the change in length of the spring. because sometimes we're going to have an example where it's a hanging spring and it's in the y-axis, and I want to make sure that you guys understand that this delta x does not indicate that it's in the x-axis. It only indicates the change in length of the spring, okay, or the displacement of the spring. So in this case, we're going to say it went 0.5 meters. So half a meter. About that far. Give or take. All right, so I want to know how much energy is stored up in that spring to figure it out. So the equation for U elastic is going to be 1/2 times the spring constant times delta x squared. And then when I plug stuff in, I like to put the parentheses. So the spring constant was 600. The delta x was 0.5. So 0.5 times 600 times 0.5 squared. And I get 75. So 75 joules. So it's not a lot of joules. All right, now let's just verify that the units that we put in here were correct and that we actually did end up getting joules. So the units for 1/2, that's just a constant or a coefficient, so we don't need that. Like that doesn't have any units. The units for spring constant are going to be newtons over meter. And then that's going to be multiplied by meters squared. So what I end up with, if I combine these two, I get Newton times meters squared over meter. So the meter cancels with one of those, and I get a Newton meter, which is, again, a joule. All right. Any questions about that? So that was elastic energy, gravitational potential energy, and then kinetic energy. So when we have examples, like I want to give you guys a very quick peek at the type of example that is going to be on the assessment. I don't know when the assessment's going to be, but just to give you a heads up to kind of get your mind primed for that kind of problem. So there's going to be a scenario where it looks something like this. So I'm going to have a box or a ball or whatever I decide it to be, and it's going to be sitting at the very top of a ramp. And the scenario is that there's going to be 3 different states that you're going to have to figure out what the energy is to be that's present. So there's going to be a state here. So this would be state 1. And then state 2 would be when this box is down here at the flat part and there is no height from the ground and it's traveling linearly. And in my figure that I've created, I need to go find it. This part right here is a little bit longer. So it's traveling across the ground where there's no friction present. So we had to figure out what type of energy is at state 2. So this would be at state 2. And then state 3 would be the point where it has impacted the spring and then compressed it to its maximum displacement. So it's compressed the spring as far as it can, and it's the instant right before it shoots back up and goes up the ramp again. So we need to figure out what type of energy is at state 3. And then I'm going to ask you for particular things like, what is the spring constant? What is the velocity at state 2? What is the height that it started at? And we're going to end up being able to figure that out. So that's kind of just a little bit of an insight of what's going to be on the assessment. Make sense? So we're slowly building up our skills. So today was just going over the basics of what these energy equations are. Tomorrow we're going to go over figuring out how to solve for a particular variable when you're given 2 states, and quickly solving it algebraically and then getting a value. So what I want to emphasize before I let you guys go for the day is that all of the energy, no matter where it's at in the scenario, all of the energy, the total energy, remains constant, just like in that skateboard one that we showed last class. So state 1, state 2, and state 3 are all equal in value. There's no friction, there's no energy loss, there's no air resistance. All the energy is conserved. It's just converted from one state to another, or one type of energy to another. So using that piece of information, we would be able to figure out different parts of this example. Cool. Like I said, we're going to probably get to a problem like this hopefully by next week. I can't promise anything, but depending on how well you guys understood what we did today, we might be able to get to that middle to late next week. All right. Does anybody have any questions? Okay. So I'm going to add a link to Canvas so you guys can access the video that I'm live streaming right now, in case you need to go back and review it. Like I said, I don't want to put on my account on YouTube and on Canvas, because that not only just requires more work, but it's just 2 different places that I need to make sure that everything is updated. And having it on YouTube, it automatically updates. So that's where the video is going to be. Okay. And I'll provide a link so you guys can access that. All right. So if you guys don't have any other questions, then I will see you guys next class. All right.